Unlike the rigid array bookshelf where every item desperately needs its own consecutive cubby, a syncly linked list lets you operate totally differently. Imagine just throwing items haphazardly into a massive warehouse. It honestly doesn't matter where they land, as long as each item has a sticky note explicitly telling you where to find the next one. Because each piece of data tells you where the subsequent piece is hiding, there's absolutely zero element shifting required.
The secret ingredient making all this work is the node. It functions exactly like a clue in a real-world scavenger hunt. Think about it. In a scavenger hunt, you find a physical box. Inside is your prize. That's your actual data. But at the bottom of the box is a piece of paper with an address on it, and that is your pointer. You don't hold a master map to the whole entire course. You just have your current node pointing strictly to the location of the very next one.
Because we're literally just following clues, adding a new starting point to our scavenger hunt is blazingly fast. To add a new start, we just hand out a new clue to our players. We write down the location of the old starting point on it and tell everyone, hey, start here instead. The computer memory updates instantly. No shifting a million records down the line. Boom, done.
And it's so cool how the theoretical concept perfectly matches the Java programming. To insert the airport code LAX to the front of our flight path, the add first logic simply creates a new node for LAX, sets its pointer to the old head, which was MSP, and magically updates the official starting line. Theory and code just working together in perfect harmony.
But wait, there is a catch. Section 5, the tail removal trap.
When a tail node points to a null value, it means the scavenger hunt is officially over. But if we decide we want to remove that final destination, the very end of our list, we run into a huge problem. You see, our clue network only points forward. It's a strict one-way street. LAX points to MSP, which points to ATL, which points to BOS. You can never go in reverse. Think about it for a second. If you delete that final tail node, the second-to-last node still thinks the tail exists. It's pointing straight to a dead end. And if you can't step backward from the tail to update that previous node's pointer to null, how do you fix the list? Well, you are forced to start at the very beginning and walk through the entire scavenger hunt all over again just to find that second-to-last clue. Imagine running across an entire city following a million clues just to tell the guy at clue number 999,999 to throw his instruction card away. That is a massive, massive waste of processing power